Thank you for coming. Can you hear me? Yeah. Thank you for coming. It's my honor to be here for this 25th anniversary celebration. I want to tell you a little bit about creativity, discovery, and risk, and in the context of Nobel Prizes past and future. This is a photo of the Nobel medal, which I'm sure you're familiar with. So let's talk about creativity. And I'm going to start with a story from my childhood. I showed the first indications of creativity in physical science in 1940 when I was 4 years old. And I know I was 4 years old because my mother wouldn't let me cross the street yet. I hadn't started school. But I had a birthday present. I was playing on the sidewalk in front of my house with a set of toy soldiers that I had received. All boys like to do such things. There was a special feature to my toy army. It had a cannon. And the cannon had a little mechanical switch, and you could fire a missile. Really, it was just a small stick. So the game was to put the soldiers out and shoot and try to knock them down. Well, I quickly learned some physics. I quickly learned that if you tip the cannon up a little bit, it would go farther. Or if I put the cannon on the first step of above the sidewalk, it would do better. I was having a good time, but as you know, little boys become quickly bored. And I had an idea. I could use matches for the bullets. Instead of using just a small stick, I could use a match. So I went in the house, I got a book of matches, and I thought they would explode. When they hit the sidewalk, they would light. And it would be more real. Vision was very clear in my mind. So I went in the house, I found a box of matches, and the fun began. The very first match that I shot burst into flames as it hit the sidewalk. I was having a wonderful time. Of course, I got caught in the act. My mother shut down the operation. But it's an example of perhaps the greatest pleasure of being a scientist is to have an idea, then to do a series of experiments which demonstrate the idea was correct, to demonstrate that nature actually behaves as conceived in the mind of the scientist. This is the first time I ever had that experience. I've been fortunate to have that experience many times since, but it's really the essence of creativity in science. My experiment with the cannon and the matches and the toy soldiers was the first time I experienced this pleasure, but it really was creativity. I had an idea. I used my limited knowledge of the way the world works. Artillery shells explode, matches light when struck, and I created my own special reality. So in science, creativity and discovery are related, but they're not the same. Scientific breakthroughs typically result from a combination of the two. Look at a couple of examples. Watson and Crick deduced the structure of DNA based upon a few important hints obtained by the experiments of Rosalind Franklin, as you all know. Their first accomplishment was to understand the importance of the problem and to have the audacity to believe they could solve it. This famous photo you've seen many times, sort of a tinker-toy model of the structure of DNA. And the paper that they wrote was perfect. It's 1 page long. If you've never read it, you should read it. And the last sentence in that famous 1-page paper says it has not escaped our notice that the specific pairing that we have postulated immediately suggests a possible copying mechanism for the genetic material. And there was the creative step. By discovering the structure, they realized that the double helix contained the secret of life. It took a few years for that to be cleared and the genetic code to be translated, but they had done it. There are many examples of this kind, and indeed many of these resulted in Nobel Prizes. Arno Penzias and Robert Wilson made a marvelous discovery. Their creativity was the invention of a better technology, a very low noise microwave amplifier. And they wanted to see if the performance of this amplifier was as good as they expected it to be. So they took it out at night and they pointed it up to the open sky. And to their surprise, the noise was much bigger than the design. And so they realized it wasn't noise at all. It was a black body radiation that was left over from the Big Bang at the beginning of the universe. And they were awarded the Nobel Prize for that. This picture I don't have to tell you about. Einstein created the general theory of relativity by imagining what happens in an elevator as it might be falling. He realized that the light would appear to curve. And from that simple conceptual obligation, he created the idea of curved space-time as equivalent to and the origin of gravity. When during the solar eclipse of 1919, light was observed actually to curve around the sun, stars appeared to be in a different place, Einstein became deservedly famous. And 2 weeks ago, it was just announced that the gravitational waves were detected for the first time, 100 years after his first prediction. That was an amazing result. And even in the newspaper, they said gravity waves, but they also said fluctuations in curved space-time, pretty sophisticated for a newspaper report. I must say, as a scientist, I was really proud that day, even though it had nothing to do with me. The exquisite experiment that was done to detect these gravitational waves, the motion involved in this big detector was half of the thickness of a proton, half the dimensions of a proton. And the experimentalists could detect that. So my experiments with the cannon and the toy soldiers were the first indications that I might have a future as a scientist. Many years later, Alan McDermott, Shirakawa, and I had the idea that we could make polymers, plastics, long-chain molecules that would conduct electricity and exhibit the electrical and optical properties of metals and semiconductors. I'm having trouble here with my voice, I'm sorry. Excuse me. This is a picture of the three of us together. And our subsequent discovery of metallic levels of conductivity, electrical conductivity, in the polymer polyacetylene demonstrated that our ideas were both true and revolutionary. The field of semiconducting and metallic polymers had been created. Now, before that time, polymers had been studied by many people. Famous names of Staudinger, Ziegler, Natta, and Fleury. All those polymers were insulators. And they were uninteresting from the point of view of electronic materials. But class of polymers that we discovered combine the electrical and optical properties of metals and semiconductors with the processing advantages of polymers. These are a photograph. This is a photograph of several different polymers in solution. They have different colors because they have different molecular structures. And those different molecular structures give rise to different transparencies. This is the fourth generation of polymeric materials. So, discovery and creativity. What about risk? Well, in the beginning, these were dirty materials that were complex and poorly characterized. My physicist friends thought I was crazy to work on such a problem. We tried to mitigate the risk, but the attraction was the quasi-one-dimensional electronic structure of linear electronic polymers seemed to me particularly interesting. And of course, there's the potential for useful materials, plastic, metals, and semiconductors. The early materials, polyacetylene, were unstable and intractable, but to mitigate the risk, we chose the simplest possible polymer. This is the polymer of acetylene. And if you look at the electronic at the structure here, each carbon is bonded to one hydrogen and two other carbons, and carbon has a valence of 4. So there's one electron left over, and that electron could be anywhere. And that suggests that polyacetylene could be a metal. What happens in reality is these two form a weaker bond, these two form a weaker bond, and we have this bond alternating structure, semiconductor. Now, today there are hundreds, literally, of this class of materials with bond alternating structures. I've shown a few of them here, but literally hundreds. And it was discovered that if you put thin film of these polymers between two electrodes, they gave off light. So that opened an entirely new dimension for polymers. Different colors here are because of the different molecular structures. Plastic substrate. This is the first step toward roll-to-roll fabrication. And I am told that now real TVs are being demonstrated with flexible, completely flexible. This is the first one. That's my hand. That's my ring. I recognize it. Now we have full-color PLED displays made with small molecules today, primarily, but printed, and it's a whole industry being born. I was telling a few students a while ago that great discoveries can be found by exploring new directions in interdisciplinary science. moving into new directions requires going beyond one's core of knowledge. Therefore, it involves serious risk. Might make a mistake. I lived with that risk for 24 years. And during that 24 years, created a field at the boundary between physics and chemistry. I was born a physicist. People tell me I look like a physicist. But we are what we have become. And with the award of the Nobel Prize in Chemistry in 2000, I became a chemist. This is a Nobel Prize is always given on the 10th of December because that was the anniversary of the death of Alfred Nobel. And this is the way it looks. It's the way it looked that year. That's me. Here's the King of Sweden and the Queen of Sweden. And this woman now is the Crown Princess. The band plays a great ovation, and one is supposed to walk over and meet the king here in the center, take from him the scroll and the medal. So after 24 years, we had indeed discovered the metal-insulator transition in these materials, demonstrated one-dimensional physics of a special kind, solitons and polyacetylene, and there was a promise of real applications. This is the image of that moment. What you're supposed to do, take the prize from the hand of the king, shake his hand, and don't drop the prize, and then you're supposed to bow to the king. And then you're supposed to turn to the academy. You're supposed to turn and bow to the academy, and then you're supposed to turn and bow to the audience. And I did that. I made no mistakes. Picture of my wife and I celebrating afterward. The next year was the 100th anniversary of the Nobel Prize. So I was invited to come back. And that was the year of Bose-Einstein condensation. And the first physics prize is always given first. And in alphabetical order. And the young man who first received the prize went to the king, took the prize, and just turned around and walked away. And he took 2 steps, and I was there, I saw it. He said, not out loud, but he mouthed the words, shit. But it was too late. So he missed his chance to bow to the audience in a proper way. We were happy. Here's a picture of that. I had a nice scotch. So these are, I'm pointing out to you here that these solutions are not just colored liquids. They can be formulated as inks with electronic functionality. Gutenberg invented printing in 1545. Today, scientists and engineers in laboratories all over the world are actually printing electronic circuits. They're printing light-emitting displays, and they're printing solar cells. Solar cell is one of my current passions, and my colleague, Henrianne, is certainly doing beautiful work here on printed solar cells. I think I needn't tell you about the importance of the power from the sun. This is going to be, it must be a significant contribution to our energy needs. We get in 1 hour on the Earth enough energy to run all the things that we run. We get 1 hour enough for a whole year, but we have to harness it into solar cells to convert sunlight into electricity. There are two problems. Maybe there are more than that, but two principal problems are cost and area. And by printing like a newspaper in a roll-to-roll fashion, you can make a lot of area at a low cost. So there are a wide variety of materials involved, small molecules, polymers, and there's been a lot of progress. You can see these demonstrations, roll-to-roll manufacturing of a plastic solar cell. Here in a parking lot on top of a structure which is not very strong. You couldn't put silicon solar cells there, but the very light, flexible nature of the polymer solar cell gives us advantages. You can imagine greenhouses like this with the solar cells powering in a remote place the pumps and the fans, etc. So there are many applications that are important there. This, I think, still exists. It's in San Francisco. It's at a bus stop. And the solar cells are the roof, and they light up the sign at night, or you can charge your cell phone there. One of the applications which is particularly attractive is as windows. So you can see through that. You can make a semi-transparent solar cell, put it in the window. It lets let smaller amount of light come in, so you need less electricity for air conditioning, and you can still see out and generating power at the same time. These are some examples of things that we did to demonstrate that utility. This is a little technical, but what happens is that light comes in, excites the molecule, and then in a remarkably short time, you get charge transfer, and then convert the light into electricity. The structure of this solar cell is shown here in this cartoon. Polymer in white, fullerene and acceptor in black, and it's a composite, complex structure, but you get electricity out. Now, in order to understand the importance of this very fast time, you just have to realize that there's no other process that competes with 50 femtoseconds. So the probability of charge transfer is essentially unity, and it's that fact which is the foundation of the entire field. Now, in reality, this is what the material really looks like. This is electron microscopy in tomography mode. But you can see the black fullerene and you can see the white polymer. And you can see that there are pathways of both throughout the thickness of the film. Every one of these little junctions between the two is a heterojunction where charge is separated. Every one of them is a microscale solar cell. So we pursued this. We found that this occurred in timescales that are almost unbelievable, 20 femtoseconds. Lauren Cake was the one who really discovered this. So it's nearly instantaneous, and that gives us a chance to make a high-efficiency solar cell. The origin of that ultra-fast transient absorption comes from fundamental quantum mechanics. It comes from the uncertainty principle. And that makes it even more interesting to me as a physicist, that it's really deeply involved in the origins of quantum mechanics. So there are two time scales here. There's a very short time scale and a longer time scale. The longer time scale is exciton diffusion, which many people thought was the only thing, but it's now pretty well cleared up. And as I said, the Heisenberg uncertainty principle is the origin of that ultra-fast time scale. One cannot know the location of the photo-excitation to an accuracy better than about 30 nanometers, and that's the size of these nanostructures that I showed you a moment ago. So this is an example of one of the importance of nanoscience, where we can expect the emergence of new physics. Uncertainty principle is responsible for this 50 femtosecond charge transfer. The initially delocalized nature of the wave function is determined by, and not by, a solution of the Schrödinger equation. So after the Nobel Prize, what's next? Well, entrepreneurial activities, theater activities. Mrs. Heeger and I have participated in a production of plays in the Broadway theater. I performed with my colleague David Gross in the, who is a Nobel laureate as well, Santa Barbara. We did the play Copenhagen. I don't know how many of you have seen it, but it's a very interesting play about Niels Bohr and Werner Heisenberg. I played the part of Bohr, and David played the part of Heisenberg. And we had great fun doing this several times. We did it once in Santa Barbara. We did it once in Brussels on the 100th anniversary of the famous Solvay Conference of 1912. And we did it once for the Nobel Week in 1913, which, by the way, was the 100th anniversary of Bohr's discovery of the atom. So, tried my way at acting and had some fun with it. Although I must say, I saw this play done professionally before, and I thought we were doing very well. And I saw it again done professionally afterward, and I realized we are really amateurs. But it was a fun thing to do. Entrepreneurial activities means startup companies. Let me tell you about one. We started up several companies, 5 altogether. One of them went into bankruptcy, but all the others are doing very well. One is on the stock market, currently being traded. I want to tell you about Synvenio. This is a liquid biopsy for cancer assessment, a simple blood test. It's really the ultimate in personalized medicine and an approach to cancer diagnostics. It's been known for a century that tumor cells circulate in the blood. If someone has a tumor cells will circulate in the blood. They're very rare, but they're very important because they cause metastasis. And that leads, usually to not good things. So, in the past, find out what was going on, doctors would take a biopsy. Take a piece of meat from you and analyze it and see if the cells are cancerous. The idea of Sinvenio is to take a simple blood test, and that blood test can be analyzed, and we can detect circulating tumor cells. It's very important, obviously. Over 1.5 million people are diagnosed with cancer every year in the United States. Early detection and regular screening are the key to successful treatment. Because once cancer metastasizes, chances of recovery are very poor. So what's the origin of these circulating tumor cells? A single change in DNA causes an abnormal cell. Cancer is a genetic disease. There is an oncogene, a gene which has a mutation, and that mutation growth continues for years until finally tumor is formed. When the tumor is formed, CTCs, the circulating tumor cells, begin to flow in your blood. So the secret is to capture them. Now, I'm not going to go into the details here, but let me just tell you the first experiment that was done was to take the blood from a healthy person, spike in 10 tumor cells, run it through the microfluidic system that was designed by my colleague, and we got 9 of them back, captured 9 out of 10. Secret then is that if it's pure enough, you can use PCR to amplify the DNA, and you can find out if the mutation is there. So you can find out precisely what the origin of the cancer is. In some cases, there are cures, and you can use this information. In other cases, it gives you precise information about the origin of the cancer, and people are working on cures. So we call it liquid biopsy, a simple blood draw. We actually trademarked the name, and it's becoming very popular in the literature, liquid biopsy, because it doesn't hurt. You don't have to go to the hospital. You don't have to take a real biopsy. And the process is relatively simple. You go to the doctor, take a small vial of blood like you do regularly when you have a physical, put it through the microfluidic system that was designed, amplify the genetic material, and then you analyze the mutations. That kind of information comes back to the doctor and it results in a treatment. This process takes just a few hours. So the ability to capture these circulating tumor cells opened up the possibility of a non-invasive, painless with low risk, and it's inexpensive with quick turnaround. Diagnostic. I don't think I want to describe the details, but why is it important? Well, one example is in breast cancer. In the US alone, there are 2.5 million women who have survived breast cancer. But of course, they worry about the metastasis. They worry whether it's going to come back. Well, now we can give them a test every 3 months or every 6 months, and that will give them peace of mind. This is important also because because drugs for approaching cancer are very expensive. Insurance companies don't want to pay for it if it doesn't have efficacy. And we can monitor whether it is having an effect by doing periodic liquid biopsy. Found a way to stabilize the blood so it could be shipped anywhere. And we now have started a company in China doing patients in a Beijing major cancer hospital, where we'll get a lot of data in a short time. So this is becoming reality. We have a laboratory where we're testing people now. So it's been a interesting ride from discovery to success, and eventually to the Nobel Prize. With all the other things that I mentioned, it's been a very wonderful life. But perhaps I should close with some advice to young people in this room, the Nobel laureates of the future. Cherish creativity. That's the beginning. Creativity is at the heart of any important discovery. Be bold. Have the audacity and the courage to seek to discover and to believe that you can discover. And you can. Remember, however, that creativity and discovery necessarily involve risk, because you can go wrong. But you have to be willing to take that risk. And dealing with that risk is part of the thrill and the satisfaction of living a life of science. It's not boring. It's exciting and it's scary, but it's very fulfilling. If you want to learn more about me, this book just came out. You can buy it on Amazon. You can buy it on Amazon Kindle and Apple iTunes. And I'm getting good response, so I hope you would enjoy it if you have a chance to look at it. I'm happy to answer any questions. And that's all I'm going to say.